40 light-years from Earth, in the constellation Aquarius, lies a star so faint it eludes the naked eye, yet it holds secrets that could reshape our understanding of the universe. TRAPPIST-1, a red dwarf discovered in 1998, is a cosmic enigma, a star barely larger than Jupiter but anchoring a system of 7 Earth-sized planets. This compact stellar family, revealed in 2017 by a team using the Transiting Planets and Planetesimal Small Telescope, or TRAPPIST, has ignited the imaginations of scientists and dreamers alike. Unlike our Sun, which dominates its planetary neighborhood with blazing intensity, TRAPPIST-1 is cool and dim, its reddish glow casting a faint light across worlds that orbit closer than Mercury does to our Sun. These planets, labeled TRAPPIST-1b through H, are packed into orbit so tight that their entire system could fit within the orbit of our innermost planet. 3 of these worlds, E, F, and G, reside in the star's habitable zone, where conditions might allow liquid water to pool on rocky surfaces, a tantalizing hint at the possibility of life. Red dwarfs like TRAPPIST-1 are the universe's most common stars, making up roughly 3/4 of all stellar objects. They burn slowly, with lifespans stretching tens of billions of years, far outlasting our Sun's projected 10-billion-year life. Their small size and low temperature mean their habitable zones are remarkably close in, often just a few million kilometers from a star's surface. For TRAPPIST-1, this zone spans roughly 0.02 to 0.06 astronomical units, a fraction of Earth's distance from the Sun. This proximity creates unique challenges for the planets. Their tight orbits result in short years. Some complete a full revolution in just a few Earth days. Yet, this closeness also means they are likely tidally locked, with one side perpetually facing the star's dim light while the other remains shrouded in eternal darkness. This creates stark contrasts, one hemisphere bathed in constant reddish glow, the other frozen in shadow, with a narrow twilight zone, or terminator, potentially offering a temperate haven where life might take hold. The discovery of the TRAPPIST-1 system was a triumph of modern astronomy. Astronomers used the transit method, observing tiny dips in the star's light as each planet passed in front of it. These dips, like fleeting shadows, revealed not only the planet's existence but also their sizes and orbital periods. By analyzing the light curves, scientists estimated that all 7 planets are roughly Earth-sized, with rocky compositions suggested by their densities. The habitable zone planets, E, F, and G, are particularly compelling. Planet E, for instance, receives about the same amount of stellar energy as Earth does from the Sun, while F and G are slightly cooler but still within the range where liquid water could exist. These findings, confirmed by NASA's Spitzer Space Telescope and ground-based observatories, marked a turning point in the search for worlds beyond our solar system. Never before had astronomers found a single system with so many Earth-like planets, all orbiting a star close enough for detailed study. Yet, the TRAPPIST-1 system is no paradise. Its host star, though long-lived, is volatile. Red dwarfs are prone to stellar flares, sudden bursts of X-rays and ultraviolet radiation that can bathe nearby planets in high-energy particles. For TRAPPIST-1's planets, orbiting so close to their star, these flares pose a significant threat. A single powerful flare could strip away a planet's atmosphere, leaving its surface exposed to harsh radiation. Without a protective magnetic field, akin to Earth's magnetosphere, these worlds might struggle to retain the gases necessary for life. However, the planet's rocky nature and potential for geological activity offer hope. On Earth, volcanic activity and plate tectonics help regulate the atmosphere and cycle essential elements. If TRAPPIST-1's planets have similar processes, they might replenish lost atmospheres, creating resilient environments where life could adapt. The possibility of life on these worlds hinges on more than just water. Atmospheres play a critical role, acting as shields against radiation and moderators of temperature. On Earth, our atmosphere scatters sunlight, regulates heat, and protects us from harmful cosmic rays. For TRAPPIST-1's planets, the composition of their atmospheres, if they have them, remains a mystery. Could they harbor nitrogen, oxygen, or carbon dioxide, like Earth? Or might they hold exotic mixtures, shaped by their unique environment? The tidal locking of these planets adds another layer of complexity. The star-facing side could be scorched, with temperatures high enough to vaporize rock, while the dark side might be a frozen wasteland. The terminator zone, where day meets night, could offer a delicate balance, with moderate temperatures and stable conditions. Hey, liquid water might pool, and life, if it exists, could thrive in a narrow band of habitability. To unravel these mysteries, astronomers rely on tools far beyond the capabilities of earlier generations. The James Webb Space Telescope, or JWST, stands at the forefront of this quest. Launched in 2021, JWST is a marvel of engineering, designed to peer deeper into the cosmos than any telescope before it. Unlike its predecessor, the Hubble Space Telescope, which primarily observed invisible and ultraviolet light, JWST is optimized for the infrared spectrum. This makes it ideal for studying distant, faint objects like TRAPPIST-1 and its planets. Its 6.5-meter primary mirror, composed of 18 gold-coated hexagonal segments, collects light with unprecedented precision. A 5-layer sunshield, the size of a tennis court, keeps its instruments at a frigid -233°C, preventing the telescope's own heat from interfering with faint infrared signals. Positioned at the second Lagrange point, 1.5 million kilometers from Earth, JWST enjoys a stable vantage point, free from Earth's glare and thermal interference. JWST's instruments are tailored for exoplanet research. The near-infrared camera, or NIRCam, captures detailed images of distant worlds, while the mid-infrared instrument, MIRI, probes the thermal signatures of planetary atmospheres. The near-infrared spectrograph, NIR-SPEC, is particularly crucial. By dispersing light into its component wavelengths, it can identify the chemical fingerprints of gases like water vapor, methane, or carbon dioxide, potential indicators of life. For TRAPPIST-1's planets, JWST's ability to analyze starlight filtering through their atmospheres during transits is a game-changer. This technique, called transmission spectroscopy, reveals the molecular composition of a planet's atmosphere by detecting which wavelengths of light are absorbed. A spike in water vapor or organic molecules could hint at biological activity, though distinguishing between life and abiotic processes remains a challenge. The TRAPPIST-1 system offers a unique opportunity because of its geometry. The planet's orbits are nearly edge-on from our perspective, causing frequent transits that JWST can observe. Moreover, the planet's gravitational interactions cause slight variations in their transit timings, a phenomenon known as transit timing variations. By studying these variations, astronomers can refine estimates of each planet's mass and density, shedding light on their internal structures. Are they rocky like Earth, with iron cores and silicate mantles? Or do some harbor vast subsurface oceans, like Jupiter's moon Europa? These questions drive the scientific campaign to study TRAPPIST-1, with JWST leading the charge. The system's proximity, 40 light-years, is a cosmic stone's throw, makes it an ideal target. Yet, its challenges are formidable. The star's phase, which can occur multiple times per day, could erode planetary atmospheres over millions of years. If life exists, it might require extraordinary adaptations. On Earth, extremophiles, organisms thriving in harsh conditions like deep-sea vents or acidic lakes, offer clues. Bacteria like Deinococcus radiodurans can withstand intense radiation by rapidly repairing DNA damage. On TRAPPIST-1's planets, life might employ similar strategies or rely on subsurface habitats, shielded from stellar outbursts. Liquid water, if present, could exist in underground reservoirs, insulated from the surface's extremes. These possibilities make TRAPPIST-1 a natural laboratory for testing theories of habitability in environments vastly different from Earth's. Beyond the science, TRAPPIST-1 stays deeper questions. What does it mean to find life elsewhere? Would it resemble Earth's microbes, or could it be entirely alien, with chemistries we can't yet imagine? The search for life is not just a technical pursuit, but a philosophical one, forcing us to confront our place in the cosmos. If TRAPPIST-1's planets are barren, they still teach us about the conditions that make Earth unique. If they harbor life, even in its simplest forms, they suggest the universe might be teeming with it. Each observation brings us closer to answering whether we are alone, a question that has haunted humanity for centuries. The TRAPPIST-1 system is not alone in this quest. Other exoplanet discoveries, like those from NASA's TESS mission, have expanded the catalog of potentially habitable worlds. Stars like LHS 1140 or K2-18 host planets with promising characteristics, but TRAPPIST-1's seven-planet system remains unmatched in its density and accessibility. Its planets' close orbits create a dynamic interplay, with gravitational tugs shaping their evolution. This resonance, where orbital periods align in simple ratios, stabilizes the system but also complicates its dynamics. For instance, Planet E completes 3 orbits for every 2 orbits of Planet F, a relationship that influences their climates and potential for habitability. JWST's observations of TRAPPIST-1 are just the beginning. Future telescopes, like the European Space Agency's Ariel mission, will focus exclusively on exoplanet atmospheres, building on JWST's findings. Ground-based observatories, such as the Extremely Large Telescope in Chile, will complement space-based efforts, though they face limitations from Earth's atmosphere. Together, these tools form a global network, each contributing pieces to the puzzle of life beyond our planet. The data they collect, light curves, spectra, transit timings, translate into insights about planetary composition, climate, and potential biosignatures. The study of TRAPPIST-1 also highlights the interdisciplinary nature of modern astronomy. Astrophysicists model stellar behavior, planetary scientists analyze geological potential, and astrobiologists speculate on life's requirements. Engineers, too, play a critical role, designing instruments that push the boundaries of what's possible. JWST's Sunshield, for instance, required materials that could withstand the vacuum of space while folding compactly for launch. Its mirror segments, aligned to within nanometers, demonstrate precision that borders on the miraculous. These technological feats enabled discoveries that were unthinkable a generation ago. As we probe TRAPPIST-1, we also refine our understanding of habitability. Earth's blueprint, liquid water, a protective magnetic field, a stable star, may not be the only path to life. TRAPPIST-1's planets challenge us to think broadly. Could life thrive in the twilight zone of a tidally locked world? Might subsurface oceans, shielded from radiation, host ecosystems? What role do stellar flares play in either destroying or catalyzing life? These questions extend beyond TRAPPIST-1, informing the search for life across the galaxy. The Milky Way contains billions of stars, many with planets. If even a fraction of red dwarfs host habitable worlds, the number of potential life-bearing planets could be staggering. The cultural impact of TRAPPIST-1's discovery is profound. Named after a Belgian telescope and playfully referencing Trappist beer, the system captures the human spirit of exploration. It reminds us that science is a collaborative endeavor, crossing borders and disciplines. The public's fascination with TRAPPIST-1 reflects a universal curiosity about our cosmic neighbors. Artists have imagined its planets as crimson-lit worlds with jagged landscapes, while writers speculate about civilizations that might call them home. These visions, though speculative, fuel the scientific drive to explore further. Looking ahead, the next decade promises breakthroughs. JWST's observations of TRAPPIST-1 will yield data on atmospheric compositions, potentially revealing biosignatures. Future missions could deploy small spacecraft to nearby stars, carrying instruments to probe exoplanets directly. Concepts like Breakthrough Starshot, which aims to send tiny probes to Alpha Centauri, hint at the possibilities. While such missions are decades away, they underscore the trajectory of human ambition. Each step, whether a new telescope, a refined model, or a daring mission, builds on the last, bringing us closer to understanding our place in the universe. TRAPPIST-1's planets, with their tight orbits and fiery star, are not Earth's twins, but they don't need to be. They represent a spectrum of possibilities, from barren rocks to worlds teeming with life. Their study challenges our assumptions and expands our imagination. As JWST peers into their atmospheres, it carries the hopes of a species eager to know what lies beyond. The answers may not come quickly, but the pursuit itself is transformative. It reminds us that the universe is vast, complex, and full of potential, waiting for us to explore.